astronomy at very low frequencies, frequencies that are very hard on the Earth because of the ionosphere and transmissions at low frequencies. We can do far infrared astronomy, thanks to the lack of an atmosphere. Optical astronomy, at high precision resolution, again, thanks to lack of an atmosphere. And even gravitational wave astronomy. So I'll mention many of these things as we go along very briefly, but to give you some flavor of what the future holds in store for us. So let's dive into cosmology. So the major breakthrough in modern cosmology came about really with the work of George Lemaitre, following on that of Friedman and Einstein, of course. But it was Lemaitre who, as early as 1927, developed a series of models for the expanding universe, in which there was initial deceleration as time went on. And in some of these models, some collapsed, but others went on to expand forever and even accelerated. So our modern interpretation, of course, is that this deceleration is due to the presence of dark matter, and the acceleration at late times in some of these models is due to the presence of dark energy. But maybe what is not so widely known is that in addition to Lemaitre analyzing the same data that Hubble analyzed actually, and finding empirical evidence along with Hubble, independently of Hubble, for the expansion, he was also very much aware of the notion of dark energy. And so here is a quote from a paper that he wrote in 1933, in which he was very much aware of the quantum fluctuations of the vacuum. And he talked about the equation of state. You see here, he talks about pressure being minus rho c squared. And this is what we now call dark energy in the vacuum. And this is what will give you, since ordinary pressure, positive pressure, is what is causing eventually the collapse of the universe or the slowdown of the expansion, the opposite accelerates. And that Lemaitre was amazingly aware of this. So, and initiated our modern discussions. So imagine this happened, 90 years ago. It's really quite incredible. So what I want to talk to you about really is what has happened since, very, very briefly. Here is our modern view of the universe. So the major cosmology development post-Lemaitre, of course, was the prediction of inflation, which takes us from a universe of arbitrarily small scale to the vast universe that we have now by an early phase of exponential inflation. We can see back all the way to the microwave background, last scattering epoch, a few 100,000 years after the Big Bang. Here we are now, we're looking back into the past. The galaxies form as time goes on. Before the galaxies, there were the dark ages, where we're just beginning to explore more about that. And the microwave background, when we look at the fluctuations on the sky, we're exploring the seeds of structure now. So all of that is wonderful. And that is the modern context of cosmology. But we have somehow to prove this, or be happy that we actually have a robust and verifiable theory, especially of the beginning. We can see back this far to the fluctuation of the microwave background, but what happened before is somewhat of a mystery, although with very strong theoretical conjectures. So how much better can we do? Well, what are the ingredients that we need to make this cosmological picture really be robust? We need to understand what the dark matter is. This is responsible for the force that holds the universe together. We have no detection of it. That's a worry. What about the dark energy? It was just a constant in Einstein's equations. the cosmological constant. Is that a reasonable hypothesis? Do we understand where this comes from? We have no, and maybe it's not even really constant. We have no understanding of this. So these are issues that we have no immediate prospect of improving, as I will show you in a second. There are interesting other possibilities, predictions from the inflation theory, which we really need to verify. One is there should be a gravity wave background produced at the end of inflation from the intense shaking of the universe as the inflation phase is ended. This is communicated to the microwave background in terms of shearing modes, tensor modes. And so major experiments now are searching to measure this. Galaxy formation in our standard model of the universe is driven by the presence of dark matter, which effectively is cold. This means it clumps on small scales. And as time goes on, these aggregate into bigger and bigger scales. This bottom-up theory does lead to a prediction of spectral distortions in the microwave background. This we haven't seen yet. And then finally, what I think is the most exciting and most robust of these predictions, as I will show you in a second, is that initially the universe was not just randomly Gaussian. And so this cartoon takes you from inflation to the present day universe and the various fluctuations that we have in the galaxies, for example, are probes of the beginning. And so here is, for example, what we call the two-point correlation, which is, random Gaussian fluctuations lead to this, and it's been a wonderful probe of structure of the universe. But there are complex patterns, higher order fluctuations, which we call non-Gaussianity, primordial non-Gaussianity, and inflation routinely predicts these. They're sort of higher order, if you like, in temperature fluctuations, inevitably therefore non-Gaussian because of that. And but it's a robust prediction of almost all inflation models, it seems. So we'd like to understand this better. Okay, so that is my brief overview of where we are now. And so let me focus on the amber zones here to see where we're going. But first, I'll just summarize where we are somewhat stuck at the moment. Okay, so let's begin with dark matter. We have this wonderful landscape where we can search for dark matter. First, we think it's an elementary particle, something that interacts very weakly. That's our best bet. And this shows you the full range of particle interaction strengths and particle mass, and the landscape is incredibly vast. These are many orders of magnitude, logarithmic scales. And so this is a sobering vision of where we might be looking. We have no idea where the dark matter might be hiding. So we do have some reasonable theories, and here's a list of them on the left. Dark matter may be thermally produced or whatever, or even be ultralight. And so this leads us to preferred areas of this vast parameter space. And you can think of these as the most motivated areas. So rather than search everywhere, which is totally impossible, we need, and experimentally, it's just too vast a range to contemplate today anyway. We focus on areas where we have developed techniques that can look in more detail. And these range from, many GeV particles to incredibly light particles. These are the ranges. And the theories behind looking here are also rather plausible theories, including, the idea that there is some sort of universal symmetry at the beginning, the fact that string theory and QCD lead to various, and quantum theory lead to various preferred areas that we might try to look in. Of course, that is useful. That tells us where we might be looking. We'd like some other evidence to convince us this is the right place. One new type of evidence. So here are just some of the names of these many particles that are exotic, but some are developed to explain certain anomalies that we see in dwarf galaxies to do with the distribution of dark matter in these galaxies. So it may be that these are signatures, white dwarf galaxies, where they're great laboratories for dark matter. The smallest ones, the faintest dwarfs, have very, very high dark matter to ordinary matter ratios. So, and if we see an apparent problem there, such as the lack of universally predicted dark matter cusp in the dark matter, then we might want to blame the type of dark matter for smoothing out that cusp. So that's an option. But the problem with this approach, of course, is that astrophysics can do much the same thing. It's so complicated to form a galaxy that there's enormous feedback between the exploding stars, the black holes, and the gas that's forming the stars, that any anomalies you see might be of astrophysical origin. So that's a real problem. We can't distinguish between the two. And then lastly, we have this range schematically at the bottom, effectively non-particles, and going up all the way to the range of primordial black holes, which are actually, black holes are observed, not primordial ones, not yet, but because it's known physics as opposed to inventing slightly more exotic physics, it's a very, very popular candidate for the dark matter. Okay, so what do we do? Well, the only thing we can do is look, okay, and look everywhere we can in the particle parameter space, or even in the primordial black hole space. But so far the results are not encouraging. We haven't seen a convincing dark matter candidate yet. And it's hard to say when that will happen, but eventually I'm sure it must, but not yet. Let me switch to dark energy. Okay, here, one of the worrying issues is that we began, experimentally with this amazing confirmation of the acceleration of the universe of, if you like, Lemaitre's original hypothesis, in change into slightly modern terms at different epochs, whatever, but acceleration was what was essentially discovered at the early years of the century, and even merited with a Nobel Prize. But what I want you to notice is that the equation of state, which is what gives you acceleration, determined by this parameter W, which should be -1 for a constant, has a huge uncertainty. But nevertheless, because of the evidence mounting from dark matter and from microwave background and from supernova acceleration, basically 3 prominent axes of discovery, this was good enough to merit a Nobel Prize. Where are we today? Well, I'm taking you to the latest measurements of this W equation of state parameter and the dark matter. And you can see the error bars have gotten incredibly better. We're now looking at a few percent error bars. However, the center for all of this is still the W of -1 that was initially seemed to go along with the constant of cosmological constant. So the question is, as we go forward in time, forward the next big experiments in space, microwave background, etc., will we do any better? Is there any reason to find a deviation to identities of new physics? We just don't know. So this is a wonderful future to explore this further, but I don't think we know exactly where we'll be going. Okay, so let me turn next to the microwave background and the prospects today. Well, it's really comforting and sobering to look at the progress we've made from, and I'm going to stick mostly with space astronomy for the moment, which gives you the unrivaled view on a wide range of scales of the fluctuations from the W map to the Planck satellites. But remember, these results were basically a few microkelvin sensitivity, but we can do much better. We measured the wonderful fluctuations, but what we're looking for is the inflation signal. So here you see the temperature fluctuations, the polarization mode. This is the E mode mostly produced by foregrounds, both dark matter and both lensing and by dust. But below this, there is a shearing mode, the so-called B mode, which again, part of this comes from foregrounds, but there is a huge unknown component that will be the prediction of inflation by this red question mark. And so in space astronomy and ground-based astronomy, for microwave background work, we're going to launch in a few years the LightBird satellite and the microwave background South Pole Stage 4 project. Many more detectors, but you have to remember that one detector on the ground, that one detector in space, sorry, is worth 100 on the ground equivalently because of various technical issues. So the ultimate thing we can do most likely will be coming along from these million class detector experiments at the South Pole. But there is a problem, which is we will not be able to get to the predicted signal from inflation to much better than 1 part in 1,000. So this is the targeted value of the inflationary prediction of gravity wave modes to the density modes that we measured in the Planck satellite. However, the prediction from inflation theories is all over the place. In particular, it can be confidently close to what we'll experimentally get to in the near future, but equally, because of our total ignorance of inflation, it could be far, far smaller. And so there's no guarantee of any primordial polarization signal in the future. So we really need to think about now, I think, more robust ways. Is there any experiment we can do with a guaranteed return? Well, I think there is. And so for the next few slides, I want to take you through what I think is the new frontier in cosmology, which is the dark ages. And basically, the idea is that I will have vast amounts of information content if we can explore the dark ages. And this is from 21 centimeter radio astronomy, way back in the early universe. And all this information will give me high precision. So let me just take you through this. So here in the red, we have the cosmic microwave background, the familiar plot of the power spectrum, petering out on smaller scales because of the damping effects of the fluctuations. And we have maybe 1 million pixels in the sky, maybe a million modes, a few million modes of information content, effectively. And that limits you to the accuracy of what you can do, just the information content. So post CMB, we will have new surveys coming along, which will be measuring redshifts of billions of galaxies. And these future surveys will, it's hard to estimate how many information modes there are because galaxies are such different things, but conservatively, I would say we expect at least 100 times more modes of information content than from the CMB. But we can do much, much better. So again, notice we get more modes because we're probing smaller scales. It's as simple as that. And so now let's imagine going back to the building blocks of the galaxies. In this cartoon, you see there were millions of clouds for every big galaxy. Here, time proceeding this way. So going to smaller and smaller scales, if we could ever look at the dark ages, we'd pick up something like 1 million building blocks per galaxy, million solar mass clouds per galaxy. And that unleashes all of these modes that we can in principle see in absorption against the microwave background. And it's this information content that we will need if we really want to probe inflation rigorously. And I'd like to try to address that point and show you that a little more convincingly now. So what are we looking for? Well, imagine going back in time. Okay, here we are today, this is early on. As you go back in time, the intergalactic medium is being reionized. We get to the epoch of reionization, mostly from a combination of mini quasars and dwarf galaxies. The gas, intergalactic gas, is coupled by UV radiation, its spin temperature to the gas temperature. Remember, we're looking for a gas, an atomic gas signature to get these first building blocks. If you go back early enough, you're at an epoch in what we call the Dark Ages, basically tens of millions of years after the Big Bang, where the gas is cold enough, just because of adiabatic cooling by the expansion of the universe, to be seen in absorption against the microwave background. And so that's before there were any stars to mess things up. So this means going back to a redshift of roughly 50, basically. So anywhere between 30 and 100 will do, but the sweet spot's in the middle, and that I show you here. As you go back in time, this is the spin temperature. Remember, we're looking at hydrogen's fine structure excitations from the parallel to anti-parallel spin of the electrons. And this gives me the signature of hydrogen that I map throughout the nearby universe, but equally we can do cosmology with it. So going back in time, you can avoid, you have to go back before reionization, before the first quasars, before the first stars. And then finally, you have an epoch when the spin temperature of the gas can be seen as a shadow against the microwave background. And I want you to notice that we're looking at a few tens of millidegrees Kelvin. And we have to do this at a redshift, the sweet spot's roughly at a redshift of 50 or 60. So you have to do this at something like 30 megahertz, because we're using 1400 megahertz neutral hydrogen, highly redshifted. So how do we do this? Well, there's only one place to do this, possibly space, but I want to argue that it's the moon that will be the ultimate platform for low frequency radio astronomy and for dark ages exploration in the future. And in particular, it's the far side of the moon. Why the far side? Well, we don't want to see the Earth, that's for sure, because the Earth is a noisy radio environment. And of course, we have no ionosphere, which means you can go to low frequencies. And so the Earth, is a thing to avoid. And the far side of the moon is the most radio quiet environment in the entire inner solar system. So what do we do? Well, we build an interferometer. Now, we're good at building interferometers. This is one under construction, SKA, to work at low frequencies, but not quite as low as you need to go. It'll be good maybe at 100 megahertz, 70 megahertz, but it won't get us to 30 megahertz because the Earth's ionosphere, basically, giving you too much of a problem. But we want to do something like this on the far side of the moon. So here's a schematic picture of printed dipoles being laid out by lunar rovers, I should say, on the far side of the moon, mylar strips with imprinted dipoles with correlators and satellites to receive the data going around the far side of the moon, then transmit it back to Earth. So this is highly schematic. It's a cartoon, obviously, but we are developing pilot projects to do just this at the moment with, up to 100 antennae. Now, you need millions. So here are some of the parameters of what you need. To go to redshift 50, you're going to observe at 10-meter wavelength. Well, that's good because you don't need to worry too much about the boulders on the moon. You need to achieve something like 100 times the resolution you can currently with a microwave background. And so that determines how many antennae and what scale you need. So the optimal array you can estimate to get to this resolution as being spanning a 100-kilometer baseline, but you need to get as close to filling this area with dipoles as you can. And that means having millions of dipoles to get the sensitivity you need. And the biggest problem of all, though, is going to be the foregrounds, because low frequency emission comes from galaxies, our own galaxy and many, many others. And the foregrounds are thousands of Kelvin, and you're looking for a 10 milligauge signal. So what is it that you can do? Well, we have a new proposal just announced in the past weeks, actually, for a funding situation by NASA, which is you want to build a huge Arecibo-type telescope on the far side of the moon. So you go to a crater, and basically you have a deployable wire mesh. This is several kilometers across with a suspended receiver. And with this lunar crater radio telescope, you can now look for the sources and basically take out a lot, hopefully, of this horrible background that will make it so hard to look for the dark ages. So that's amazing. I think this is the way we'll be going, a combination of interferometers and telescopes, not tomorrow, but we're talking about the 10, 20-year time frame. So what is it that we want to do with this futuristic telescope system? We want to detect primordial non-Gaussianity to probe inflation. It's a major prediction of essentially all inflation models. So I've argued that for dark energy and dark matter, we don't have a robust way forward, likewise for the CMB, but we do for non-Gaussianity if we can ever get to this amazingly weak signal, this generic prediction, which is this correction of 1%. And let me just remind you what that is. It's simple to estimate in canonic inflation models, single field, slow rolling models, but this is a guideline for more complex models. It just involves the scalar spectral index, which is well measured from the Planck satellite now to 9 sigma. And so you get a certain value of this parameter, 0.01, which is this quadratic correction to the temperature fluctuations. Where are we today? Well, we're not doing very well compared to this prediction. The best we can do, and perhaps ever do, with the microwave background is getting current limit to something like of order 10 for this number. Maybe we'll do a little better as we put in all the polarization modes with future experiments with higher resolution, but we're never going to do as well as we'll do with galaxy surveys because they have so much more information content. But here I have 1 million bits of information. Here I have 100 million. And with this, thanks to 1/√n, I can now get to FNLs of 1. But look, my goal is 0.01. What can I do? Well, here is the beauty of the far side of the moon. I can get trillions of modes. I can beat down FNL to 0.01. And what I want to emphasize to you is it's not just one number. What I'm getting is from inflation stretching my primordial quantum fluctuations onto the CMB and galaxy structures. That's fine. But now I can probe the dark ages and get the complex patterns, the higher order correlations that are clues to the beginning of the universe. So that is where I think we're going in cosmology in the future. Okay, so I want just to tell you one more brief thing, really, and that is that we can do so much more in cosmology than just this remarkable probe of inflation. There's a lot more to do from the moon. And I'll go through that briefly because this is a subject that is meant for all of astronomy, not just the cosmologists. So what is the framework for this? Well, here are some of the craters near the South Pole, a particularly well cratered area. And you can see there are some very dark craters. And let me zero in on these craters for you. And so one in particular, and many more are studied, here's a snapshot of it, has very high rims. Now, because we're near the poles of the moon, the sun never gets very high in the horizon and never very far below the horizon. So the craters are deep enough to be totally dark all the time. They're also incredibly cold, as low as 30 Kelvin. And the rims are so high that one has essentially perpetual light from the sun just above or just below the horizon, especially when just below the horizon, which means that I have a source of solar power. So they're wonderful places to build telescopes. So I won't say anything more about the ice on the moon, the recent discoveries of that, but that's believed to be another reason for going to these dark craters as a reservoir of ice, and also will be useful in doing local construction. But let me not stop there, but go more to the astronomy. So what is it that you can do in one of these dark craters? Well, here is a goal for the distant future, but we're talking about decade, 2 decade, 3 decade timescales. We once conceived of building a 100-meter telescope on the Earth. It didn't get very far because of engineering issues. It was called the Overwhelmingly Large Telescope. That was the acronym. So why not imagine a similar project for the moon where there are no winds, there are no earthquakes, there's no atmosphere, and the gravity is much lower. So one could most likely build big structures. If you could ever do this, then, well, it's amazing. You would be able to resolve the first stars in the universe. So here is, you could get a fraction of a parsec resolution, which means you could certainly see the first giant H2 regions, something you could around stars, star clusters, was something I don't think we're able to do in any other way. Just from the sheer diameter of this telescope giving you the resolving power that you need. Now, it turns out that this is not all. So I want to take you to another aspect of what one could loosely call cosmology, but it's really the whole astrobiology community, and that is the search for exoplanets and their biosignatures. So the other thing one could do with such a huge telescope is pick up many more candidate exoplanets with possible biosignatures of interest. They would be near habitable stars, they would have rocky cores. Our current projects in space, most likely the most futuristic being LUVOIR, are projected to have maybe 50, if it's a 15-meter telescope, which itself is, I think, questionable given funding issues, 50 targets to be followed up. But imagine building a 100-meter telescope on the moon. You could suddenly reach thousands of target exoplanets and follow them up spectroscopically. And with yields of thousands, you just need so many things to follow up before you could have a reasonable chance of finding something really interesting that might be life-related. Well, that's 100-kilometer scale, but look, there's no reason to stop there. And so here is a futuristic issue. Why not do optical interferometry? Much easier when you don't have the atmosphere to worry about, but by no means easy at all, and use that to image exoplanets. So here is one proposal, very futuristic, I admit, but there's no, I think, roadblocker at this point. And this is to build a 10-kilometer aperture hyperscope. Amazing concept by Antoine Laborie, founder of interferometry, actually, modern interferometry. So he wants to go to a dark crater, put in 5-meter telescope segments. This would actually mostly be near infrared use, and have a suspended focus and camera there. And with this amazing resolution of tens of micro arc seconds, we could get images around the nearest planetary systems. We could see the planets around Alpha Centauri at this sort of resolution, presumably, this cartoon. This would be the most amazing thing you could hope to do in terms of an exploration for potential signs of life, imaging nearby exoplanets. Again, the moon is perhaps the only serious contender for this type of experiment. So let me now go more directly back to cosmology to give you finally two more examples. So one is the spectrum of the microwave background. So I mentioned at the beginning that one could do infrared astronomy on the moon. Infrared astronomy, having no atmosphere helps a lot. So this is the best we've done to date with the microwave background. You can see this black body that is a perfect black body, no distortions to pass in 10 to the fourth. As good as we can make one on the Earth, but theory of our standard Kodak model predicts that there should be fluctuations that give you deviations to the black body due to small scale structure. The friction of the first dark fluctuations that form in the early universe, which are smoothed out by the baryons in them, smoothing out with the microwave background, conflict between gravity and electron scattering, gives you dissipation, gives you signals of distortions, which can be seen at very high wave number. So you can't hope to image these directly, but you could see them as spectral distortions. And so this is where the regions we probed so far, galaxies and clusters of galaxies with the microwave background structure. If you could ever measure spectral distortions to high enough accuracy, you could pick out a unique prediction of the cold dark matter model. So here's an experiment that might do that. I should say that this has been tried before, proposed before, but it's never succeeded. When it is so much better, 100,000 times better than the FIRES experiment, actually. And so basically you have a Fourier transform interferometer, which compares the sky observations of the black body. You'd need to cool it down to look in the terahertz range. And it could all fit in an ESA planned payload, which in 5 years will go to the moon to put down scientific payloads and other types of payloads. It's underway. It can carry up to 1.5 tons, actually. So that's being planned and people are making proposals for this now. Why not include such an interferometer? It need not focus on the sky. It will be stable. The rotation of the moon around, movement of the moon around the sky would give you the sky scanning, and you could get the desired improvement that you need to do incredible cosmology. And what is that incredible cosmology? Here's a brief summary of what you could do. So here is the intensity of the diffuse far infrared microwave background in the terahertz band. And so Pixie is the name of this interferometer that did not get funded. And this is basically what I show you here is the FIRES sensitivity here. This is the dashed line, and but the foregrounds are huge. So it's all a question of having experiments that can sort out the foregrounds. You do that with many spectral channels. Pixie could go here, and then here is what you might want to do if you could ever go to the moon. And these various lines are indicative of the science you could do. So let's just focus on the green line, for example. So that shows you the test. It's in quadrature, so these are negative, these are positive deviations, cold spots and hot spots that would give you spectral distortions. This is from the cold dark matter cosmology. But here, this wiggly line is the most amazing thing of all for me, which is you could actually hope to see the recombination of hydrogen and helium in the universe. This happens at redshifts of 1,000 to 10,000. And these recombination lines have been this amazing prediction of the Big Bang Theory, to my mind. They're the bread and butter, of astronomy recombination lines, right? Of all things, seeing them from cosmic distances would be incredible. Okay, and then there are more exotic things too, which I won't mention, but let me conclude by telling you about what we can hope to do with one more possible signature, which is gravity waves. So the moon, remarkably, is a gravity wave detector. Why? Well, it's a huge, think of it as a huge bar in the initial gravity wave experiments. We had bar detectors. They never got very far because of sensitivity issues, but the moon is a really, really stable place. There are no earthquakes on the moon. There are occasional, very minor lunar quakes, but seismologically, because of asteroids impacting, etc., but it's very quiet seismologically. So laying down a few seismometers and correlating signals would then take you to a whole new regime of gravity wave astronomy. So this is where we're going in gravity wave astronomy. Here in frequency of the gravity waves, we have the LIGO-Virgo range, which we're currently using, and some of the sources we've seen already. The future will get us to LISA, and eventually we're also exploring with pulsars, even lower frequencies. But a lot of the astrophysics is in the range between LIGO and LISA, and this is the amazing range. You can bridge this gap by looking at decihertz frequencies with gravity wave detectors on the moon. And this would enable us to explore intermediate black holes and the spiraling in of smaller ones as they come together to merge finally over here and do incredible missing physics. Okay, so that really is what I wanted to take you through. So here is my summary. The space agencies are planning space stations around the moon, lunar villages. This is infrastructure that will begin to be in place by, I would say, a decade from now. That's the current schedule. We'll have our first astronauts back on the moon probably in 2024 even. There's a rivalry between China and the US to do that. There's a huge commercial interest which is driving a lot of this in tourism, in mining water and other, mining water for rocket fuel, but mining rare earths, for example, which we will eventually run out of on the Earth in a few thousand years, some estimations, some elements. And you may think all of this is so futuristic. Well, let me just remind you that the biggest projects in science have really long lead times. And so we're planning to build a 100 TeV particle collider. It's very unlikely this will be finished before 2050. Well, we could have all of the projects I've talked about for the moon in place by then as well. And they can do cosmology that you would never achieve on Earth. And I just don't think it'd be realistic to do them in space. I'll explain why in a second. It's also an amazing pathway with these big telescopes to resolving one of our most fundamental questions, are we alone in the universe? And so could we actually do similar things without going to the moon? Well, it's budget. That's all, I think. Because we're going to the moon anyway, for these various other reasons, and you may approve of them or not as you wish, but it seems to be the future. Why not build telescopes as well? And we will do some science. The Hubble Space Telescope, I think, would not have been built without all of this wonderful infrastructure, the International Space Station, the Space Shuttle, etc. It was a few percent of the total budget. So I would say that astronomy's future is on the moon. Okay, here are some of the many projects, many space agencies competing to go to the moon, from NASA, Russia, China, and even the latest news is that NASA will be following up on the initial planning in the Trump administration to build Artemis around the moon, etc. And so there is space for telescopes. So I am looking forward to that, even though I and many of you in the audience may not be free to see this. It's very much for the younger people, the students in the audience, to help develop this magnificent future on the moon. So thank you.
Thank you. Thank you very much, Joe, for this excellent look into the future of cosmology and astronomy. Are there any questions?